All right, welcome to the second part of our notes here. Last class period, we started talking about solubility in general. We started talking about what a solution was, like a solute in a solvent, so like salt and some water dissolved together. We talked about polarity. We said that water was polar, and that polar things like water are able to dissolve other polar things, like salt molecules, salt formula units, or sugar molecules. And nonpolar things could dissolve nonpolar things, like oils could dissolve other oils. Nail polish remover can kind of dissolve nail polish a little bit. The other things we talked about were some solubility rules. We said that for certain ionic compounds, it seems like some things would dissolve in water and some things wouldn't. So we could predict what could and what couldn't dissolve in water with this, like this chart of information that would be provided to you whenever you're asked to make such predictions. And then we started talking about saturation. We had three different scenarios of saturation. We said that every sort of solvent and every sort of solute, there's a limit to how much solute you can put in that solvent. And that limit is called the saturation limit. And when a solution is saturated, when it reaches saturation limit, that is when you cannot dissolve any more solute in there. When it's unsaturated, we said that means you can dissolve probably a little more solution or a little more solute in there. And when it's supersaturated, we're saying that it went beyond the limits of dissolving things. And maybe over time, maybe that solute would kind of like fall back out of the solution again. Solubility curves. Did we leave off here last time?
Yes.
Okay, so solubility curves, these are a graphical, when it's a graph, representation of the solubility of substances. And we see a very typical looking solubility curve on the right here. And you can like just take a moment to kind of like process what's going on. We have all these lines and they're labeled with different chemicals. And then you might notice that we have an x-axis that says temperature. And the temperature is in degrees Celsius. Notice it increases as we go from left to right. And then we have a y-axis that says grams of solute per 100 grams of water. So it seems like, depending on the temperature, more and more solute is there for the same amount of water that we have. So these solubility curves show how much of a solute can be dissolved in 100 grams or 100 milliliters of water, or maybe other solvents at a given temperature. So we can also notice on this graph that most of the lines, they seem to kind of go up over time, like they go up as we increase the temperature. So it seems like the solubility of a substance tends to increase as the temperature increases. Now, do any substances break this rule? It does seem like NH3 really noticeably breaks this rule. It tends to have a very obvious downward slope. So we're going to say NH3 breaks it. This is also known as ammonia. And why does this break this rule? That's actually because it's a gas. Everything else is a solid dissolved in liquid, and NH3 is actually going to be a gas dissolved in liquid. Now, on these solubility curves, the line itself, that line or that curve, indicates the concentration of a saturated solution, or as we said before, the maximum amount of solute that can dissolve at that specific temperature. And values on the graph under any sort of curve represent an unsaturated solution for that specific curve, that specific chemical. So that means that, more solute could be dissolved at that temperature if we tried to dissolve it. All right, so let's answer some example questions that could be asked about solubility charts. Which solute is the most soluble at 10 degrees Celsius? Okay, so you can look at the temperature here, 10 degrees Celsius. Kind of go up here. The most soluble should be the one with the highest value. So if you go all the way up to the highest value, it does seem like that's Ki. So I can say Ki is the most soluble at 10 degrees Celsius. Which solute is the least soluble at 40 degrees Celsius? Well, very similarly, I can go to that graph, look at 40 degrees Celsius at the bottom, and I can look at the lowest curve. And it looks like that lowest curve is this random chemical. Yeah, this is Ce2SO43. So we can put that as our answer. All right, how much solute is in a saturated solution of ammonia at 25 degrees Celsius? All right, ammonia, this is NH3. It's a very common molecule to kind of know the formula of. But let's look at 25 degrees Celsius and then look up ammonia's curve. So 25 is somewhere in between here. And then if we go all the way up to ammonia, which is NH3, right here, then we can kind of go left and see how many grams of ammonia can fit into that solvent at 25 degrees Celsius. It looks like it's about 45 there. Yeah, around 45, 46, something like that. So let's go ahead and say, let's write that down. 45 degrees, it's not 45 degrees, 45 grams is what we're looking at here. Okay, so if KNO3 has 70 grams of solute dissolved at 60 degrees Celsius, is the solution considered saturated, unsaturated, or supersaturated? So just in terms of where we would expect that to be, if it was supersaturated, we would expect the grams to be above the curve. If it was saturated, we expect to be at the curve, and unsaturated should be below the curve. So let's look up 70 grams at 60 degrees Celsius, and let's look at that KNO3 curve. So 70 grams at 60 degrees Celsius. And kind of connect it here. Okay, so it seems like there's no curve there. And the KNO3 is way up here. So it looks like if we have a point that's below the curve, that is going to be unsaturated. All right, final question here. If a solution of NaCl has 20 grams of solute dissolved at 90 degrees Celsius, is the solution saturated, unsaturated, or supersaturated? So same concepts here. We just want to look at that grams, that certain temperature, and then see if it's above, below, or at the curve. So NaCl, 20 grams, 90 degrees Celsius. Okay, 90 degrees Celsius, 20 grams. We see where this connects. And then we look for NaCl. Looks like the NaCl curve is up here. So since we're below this NaCl curve, I think this is going to be unsaturated. So that's just kind of how we read this graph and make conclusions on if any sort of solution is supersaturated, unsaturated, or saturated. Questions from this section? That's solubility curves in a nutshell. Okay, our final topic with solutions is called rate of dissolution. So rate of dissolution is just a fancy thing for saying how fast something dissolves. How fast or how quickly something dissolves. So for example, if we're making some sweet tea and we're trying to dissolve a lot of sugar, how can we make the process of dissolving sugar faster? Well, you can stir it. That's one. I mean, actually stir it. Don't just look at it. You can heat it up. What else can we do? Just one other thing that not a lot of people have been getting. Well, shaking around is kind of the same idea of stirring it up. But instead of using like really big, thick sugar, we could use like smaller grains of sugar. So use smaller grain sugar, like smaller pieces of sugar, right? So think like instead of cubes, we could use grains. Instead of grains, we could use powdered sugar. So these three factors affecting the rate of dissolving, we kind of mentioned them all, but we're going to like kind of generalize this a little. So we can say these are agitation. It's like stirring is like a form of agitation. Changing the temperature, or changing the surface area. Okay, surface area of the solute. Let's talk about the surface area for a sec there. So surface area, we're talking about like, where is this solute actually dissolving? If we have a chunk of sugar and we put it into some water, I'm just going to draw a chunk to the side here. And it's underwater now. Where is it dissolving? Well, it's dissolving on the surface of the chunk of water, right? And that's where the water is kind of like breaking that apart and spreading it apart into that solution. So if you have more of the surface exposed, that means the faster your dissolving is, or the quicker it's dissolving. So what would dissolve faster, a cube of sugar or crushed sugar? Crushed sugar for sure. I just want to elaborate on surface area for a sec. Let's say I break up this like chunk of sugar to like 3 different little chunks instead. So, the same amount of sugar, but now we have much more sugar being exposed to the water. So kind of like some random unit I'm going to make up here. But like on the left, you see there's only like 4 arrows of exposure, like 4 arrows of surface area. And then on the right here, we see there's like 1, 2, 3, 4, 5, 6, 7, 8, like 9 arrows worth of surface area, or 9 arrows worth of exposure of that solute to the solvent. So if you're exposing more at a time, then you're able to have more done. You're able to dissolve faster. Okay, point 2, agitation. So agitation, such as stirring, basically like, zhuzhing up this solution here, mixing or shaking, that removes any sort of newly dissolved particles from the surface of the solid and continuously exposes that surface to fresh solvent. So it really helps keep things moving, make sure that your solute is able to dissolve a lot faster. Finally, we have that temperature. So why would temperature change our rate of dissolution? Well, higher temperature means our particles are all moving around faster. It causes the solvent to move more rapidly, and that increases the rate of dissolving for most of our solid solutes, like salt, sugar, things like that. But it's going to decrease the rate of dissolution of gases. Okay, so higher temperatures will actually decrease the rate or the solubility for gases because the molecules move too quickly. And they're going to start to escape your water instead of dissolving the water or whatever solvent you have. Whenever a gas moves too quickly and reaches the surface of the water, it's not going to stay in the water. It's just going to go off into the air. Like it can do that. It's a gas. It can fly. And we can see this on the solubility curves from before with a downward slope. So anything on your graph that kind of look like, ooh, it's going down like that, that's probably going to be like a gas, where we had grams on the y-axis and then temperature on the x-axis. Any questions, y'all, on rates of dissolution? You can dissolve things faster by increasing the temperature, agitating it, or crushing it up and making the surface area more. All right, I'm going to stop the recording here, and this is the end of the topic 11.1 notes. And scene. Uh-oh.